嗯，然后你再同时操作这个啊，我是啊，我是啊，对对对对。
Okay, welcome to the Province Symmetry seminar. And today we're very happy to have Yong to talk about the Witten's asymptotic expansion conjecture for WRT invariants, seven-fiber harmonic spheres, and resurgence. And I think this is the first talk that involves the hard analysis to study quantum symmetry and quantum invariants. Let's welcome.
For the invitation and the introduction. So I will talk about the Witten's conjecture first. So this is a Witten's conjecture. This is a very general one. And so we want to think about the level K of unity. What is the asymptotic behavior? And in this conjecture, you can see S should be the transcendence value. And if we are working with SU2 gauge theory, this should be transcendence value in SU2 gauge group. And for each value, there exists one power series attached to it. So this is the transcendence. This is the WRT invariant asymptotic expansion. And the key point here is to prove the transcendence value will determine everything. So if we have a transcendence value, we can compute what is the attached series. This is the point. And in the special case, for us, we work to find an integral homology here. This is a very special kind of three manifold. And we think about the SU2 H theory on it. And the result is something like this. I will talk about something more, but at this time, or at this moment, we can see some results. So first, the transcendence value is a finite subset in this a -1 from 0, and 0 is a trivial flat connection, and there exists only one trivial flat connection which has a transcendence value 0. And this series, when 0 is 1, when S is 0, it is Osuki series. So this is a very classical object in transcendence theory. And when 0 is, when S is not 0, in our case, every power series is actually a polynomial. So that's a very baby case, let me say, in the school picture.
So this transcendence value is a complexification there.
Yes.
Okay, sorry, what is the one? Or this is transcendence value.
Yeah, I will tell you later. So it's so you have an action, with a transcendence action, and think about the variation of the action, and think about the critical value of that action. That's a transcendence value. But I will not use the formula like that. I will use some result from some classical textbook. Okay, so the main strategy is to use resurgence theory, and resurgence theory is a tool in complex series, divergent series. But WRT invariant is real invariant. So let's say it only has a WRT invariant with take values on the roots of unity, and you only have values on the boundary. There's no values inside or outside, and our first goal is to find appropriate classification of the WRT invariant, and the good candidate is called GPPV invariant, or Z hat invariant. This is Gukov-Pei-Putrov-Vafa. So and another name is called Z hat invariant. It is a holomorphic function inside the unit disk. And we have to say that, or we have to prove when we think about the limit, when Q goes to exponential I over K, we get the WRT variant. So the limit of GPPV is WRT for level K.
This is the well-known result, or this already known?
No, we have to prove it.
I see.
Yeah, this is a conjecture. It's called a radial limit conjecture, and later I will show one recent work by Murakami, and he proved that for any plumbing manifold, this is correct. So here, this is so we if we want to prove the Witten's conjecture, we only need this limit. But you can prove something more. For example, you can prove this. This is defined by Galova extension, and you can prove this is correct. But yeah, in general, this is not known now, even for plumbing manifold.
The GPPV is defined from what manifold?
It is now it's much more general. So I think there's some definition on even the hyperbolic manifold now. Reversal. It's Park. So Park is the student of Gukov. So he defined some new invariants inside the unit disk for hyperbolic manifold. And originally it is good for plumbing manifold. Okay, so this is the first arrow. And then we talk about the resurgence property of the GPPV. The resurgence means that if you have a divergent series, you think about the Stokes phenomenon of that series. That's the one sentence introduction to resurgence theory. And we think about the Otsuki series, which means when Q goes to 1, there is a series called Otsuki series. Otsuki series. And we think about the resurgence property of this series. And the Stokes terms for us, in the end, after appropriate arrangement, Stokes terms has a one-on-one correspondence to SL2C consumer selection connection. So this is our goal. So later I will show some slides about why Stokes term. We want Stokes term matches the SL2C connections or SL2C implementation. Okay, so the last term is the most difficult part, the technical part of the last arrow. So we have to prove that when we think about the limit there, and we take the same limit, we have to say some representation vanish and some representation survive. So here you can divide the representation of SL2C by two different kinds of representation. One is SU2, and the other is SL2R. And when you think about the limit, you have to prove that the SL2R terms vanish. So only SU2 survive. And this is the full picture. Okay.
This arrow believed to be true in general.
Believed to be true in general. How general is it not?
Not the Seifert.
Oh. Yeah, I think this framework should be somehow correct in general, but I'm not sure whether it's meaningful. So for us, the technical difficulty is so later so we will deal with the building block like partial theta groups. So this is our building block. We do resurgence theory on such analytic function. So this is the form like n mu f n exponential I is over 2p. Here f is a 2p periodic. And mu is non-negative integer. So if for us, if the building block is not like this, we don't know how to deal with it. So this is the point for us. And I mean GPPV invariant for this case equals to some combination of such series. This. So later on you will see the exact formula. Okay, so the first part is some elementary part. We will talk about some solid foundation of our result. We want to distinguish which representation is SO2 and which representation is SO2. So this is the first part. And the first, this is the manifold we want to discuss. It's called central fiber integral homology Habiro. So please remember such notations because I will use it frequently. The R is number of single fibers, and we fix pairwise coprime P's, and capital P is the product of PD, and the PD hat is the product without PD, and the P. So P1 is the only only possibly even number. The others is not. And if we choose tuple Q satisfy this condition, then we can say by using this kind of surgery that the so-called central fiber integral model. And one example is this famous complexification homology here, well, actually here we don't assume p days are prime numbers. We only assume they are co-prime. And so this is a fundamental group of such manifold, and we want to talk about the representation space, modular space. So that means it's going to be the reducible map from Pi1 to G, and we have to quotient the action of G. So and G will be SO2, SL2 single main object. Understand? And this is the first result to say that all kind of homomorphism should be like this. Let me copy this. So this is the matrix we want to use. This is in SU2 or in SL2C, so we cannot distinguish the type here, but we can think about Sj. If Sj is in SU2, then we say this is SU2 representation. If Sj is in SL2C, we say
What is Sj?
Sj is some matrix. G is either SU2 or
arbitrary Sj. Arbitrary group of.
No, arbitrary elements. So the matrix should satisfy such condition. And you can see that yeah,
Yes, my symbol books or representations or you can confuse.
Yeah.
What did I know that? So,
Yes. Almost the time. Yeah, because these conditions. So H is in the center, and H will always match to I or minus I, and so this is that. Xj to Pj is that. Okay, so the first proposition is made by Anderson, Mr. that. So this is some classification of the representation of SL2C group. So this is some description of the connected component of such modular space. So you can see there are three conditions. So let me say it here. So if we only have three fibers, then we know by the last condition this number cannot be in Z. So Lj cannot be 0, cannot be Pj. And this condition is to say the second and the third is even number. So if we think some example here, so think about the 2, 3, 5, we only have two connected components, and they are labeled by these two tuples. This is the application of the result. And these tuples is exactly the eigenvalues here. So this is these tuples is for the Lj. So this is the first string is shown, and what we think about frequency 237. This will be an example we always think about. So 237, think about the modular space in gate to SL2C. We have three connected components, and we are labeled by 1, 2, 2, 1, 2, 4. Yes. Okay. And this proposition is a very interesting proposition. It is to say that if we think about these three different connected components, we can think about some point inside. If this point corresponds to SU2 representation, then there is no point inside this component such that this point is an SL2R representation. It's a fully disjoint union. So here, I mean, so what is this point? This point is one element in this space. So
This is true for any three manifold or just for self.
I think it's only for Stokes fiber. I don't know. So this is let's say it's not very easy to prove. It's something like a lucky proof. So here, if we have an SU2 representation, it means that this point is a representation, and we have to think about all the conjugacy group here. And the other point is another representation, and we quotient the group action. So if we move from here to here, we mean we move this Sj, and these 2 points are not in the same conjugacy class. So here, if we have SU2 component, for example, because SU2 is contained in SL2C, so this is SU2 component, and by using this proposition, we say that other point cannot be SL2R. And vice versa. So if we have some SL2R component inside SL2C, then other point cannot be SU2.
So do we know which of these three connected components is U2?
Yes, good. Good question. I'm sure it's now. So this is some procedure towards to your question. So first, we have to elect L to be H. So we just remove one condition. We remove H2. So L2 to LR are all even number. So we remove that condition. And we define the switch. This is sigma I. And sigma I is just map HI to PI minus HI and this P are the two features. And the sigma is a set of all compositions of odd number of sigma. Sigma. Let's see what is the result here. The result is like this. So there is a full classification because it cannot, it will never be one. So if we compute all such sigma L and the element in sigma L satisfies these conditions, then we say this is asymptotic. And if there exists one such that this is less than this, but this is very difficult to prove. We can only play the matrix. So there's no very high level technical to use. Okay, so let's see what is the application. The application is, for example, we think about 235. So we know by the proposition, we know these two components are O as U2. And for example, here I compute Y is I1 to 2 is. I think we use sigma 1, sigma 2, sigma 3, and off composition. And I compute all of them and compute the sum, and they are all bigger than 1. So this is application of the proposition. And in 237, there exists one SL2R component, which is this 1 to 6, because one of them is laughable. So here, there is some geometric, say, if we fix 3 similar fibers, and this is P1, P2, P3. So actually, you can think about the lattice, integer lattice inside this tetrahedron. And so here we know 111 is inside this tetrahedron. So this is SL2R. Inside is SL2. And outside is outside. And if you think about this picture in general, it is a higher dimension of the lattice. So you have, for example, 4 dimension, and you have to think about the inner and on the boundary. So this is a result.
Okay. Give the result again.
Yeah.
Walls of the all is larger than 1. Is it related to the fact that S2 is S3? This it has positive curvature. You can embed some positively curved polygon inside S2, but that S2R is flat, right? There's something reminding me of embedding some kind of
Like something
triangle. Yeah, something. Yeah, some polygon inside this this SU2 and SL2R as 3 manifold.
Okay.
Just a comment.
Okay.
It should be less than equal. Because
It
It cannot be 1.
It cannot be 1.
you mentioned that, you know, for SL2R, you have to include everything that's inside. Like, let's say you have 4 points, the Seifert 100, then you have to also include the piece that's on the boundary of that. I guess 3 sometimes.
You mean if I have 4 fibers?
Yeah.
So there's a higher dimension of such.
Yeah, like you have
And,
a 3 simplex.
Yes, and
So you have to also count the ones that.
and on the boundary it is 3 fibers.
Yeah.
Yes, and it can, yeah, so it cannot not be 1.
Okay. So,
Okay, so by using the proposition, we have some, yeah, some numerical check. Okay, so now this is something about the transformer theory, and this is some brief introduction, and I will not use the path integral formalism. That's the philosophy is from here. And compute the resurgence of the Otsuki series, and I will tell you that why we compute the resurgence theory of this. So the partition function of WRT is like this. It's the SU2 gauge theory, and this is the transformers action, and so this is purely a path integral. It has no rigorous meaning, but after RT's work, it has some rigorous meaning. And we will use that form. We will not use this form. Okay, so here, if you think about the variation of the action, you get O curvature 0, and think about, so they are all solutions of the equation of motion, and moreover, we know the flat G connection is equivalent to the G representation of the pi1. So here we are talking about G representation of pi1, and this means that if you think about the saddle point theory of a path integral. So think about saddle point theory of path integral. You will see some. This is transformers value 0, and this is value until -1. This is the Otsuki series, and think about the Otsuki series, you will get so many different transformers value, and you can talk about the modular space attached to this value. So we are talking about this, and each component is like this. So each transformers value will give you a negative rational number between 0 and 1. And resurgence theory is a theory to say that if you only think about the trivial flat connection, then you are able to compute everything out. So this is the point. And I will show you later why we can compute everything with this special term.
You're only thinking of trivial G.
Yes, trivial is enough.
Trivial.
Yeah, and actually, if you want to use resurgence theory, you have to find a divergence series. And in this case, we only have one divergence series.
Okay.
The others are polynomial.
Right. Like if I put instantaneous inside, it would come. That's funny.
Okay. So the main theorem is like this. So if we think about, so this is something we'll define. I will show this in the next page. This WRT invariant with the fixed formula, and we will show that formula when K goes to infinity, it has a asymptotic behavior like this. And when S is 0, this is also here.
So X is
X.
first line is X and
Yeah, and I should have where is the table?
WRT
Oh, yes. I use X. I use X.
So what is the compared to asymptotic expansion?
It is for x a b n is bigger when x goes to 0. So we think about this. So if we remove I, okay. Okay. So here we can say this is completely asymptotic extension because everything except 0 value is polynomial. So you can move that polynomial part to this side and think about this x to be the subtraction of WRT and the polynomial terms. And this is a completely asymptotic extension. But if you have two divergent series, we don't know how to understand it. Actually, I think there's no very good definition for the transseries extension. So this is called in resurgent theory it's called transseries extension. And transseries has a precisely meaning, but when we think about physics paper, it's not exactly exactly the definition we want.
You said some if you have one
Divergent
seven series, this kind of asymptotic, the meaning of this asymptotic will work.
It's not work. Yeah, it's not work because you have to say which argument you are using, something like that. So think about this definition. You cannot give a definition for the two divergent series case. Okay, but here we only have one divergent series. Okay, so I will show one example in the end. And what we use is this formula. This is RT's formula on the Seifert integral. So it's a very complicated formula. You can see a P, Pj's, and this phi is some rational number related to the Witten sum. And so this is the formula, but I will not show it again. So what we use is this form, and we think about the radial limit conjecture of GPPV invariant, and we check that this is the limit. So that's all. So we will not think about this formula when K goes to this. This is a horrible task here. But let me say Hikami has some work on such formula. So he can, because here this is something like Gauss sum, and he have a reciprocity formula for this kind of Gauss sum, and he can prove something about the quantum modularity. But at that year, there's no knowledge about the quantum modularity. But he give exactly formula for 3 fibers. And moreover, for 4 fibers, there's some examples, but there's no general result for any fibers. Okay, so that is about the GPPV invariant. So we can forget what is WRT now. The GPPV invariant is something inside, and in Seifert fiber integral, it's clear it is very easy. But if you have any clumping manifold, it is not like this, but I think it's not very difficult to do the generalization. So the theory, the harmonic function inside unit disk is like this, and the chi j is determined by this generation function. We can explain everything.
What do you do philosophy to define this invariant?
It's something like a BPS. This BPS structure and PNC structure. This is from physics.
So you have another definition and you evaluate this definition and this
Yes, exactly. Yeah, they define an old Pauli manifold, and Pauli manifold is a generalized, a more general category with respect to Seifert fiber integral models here, and we restrict that to here to get structure.
So WRT SU2 simultaneous partial function, and this one is the
SL2C. So they conjecture that once they define this, this should be the particular function in SL2. So it's something like the complexify the big group.
So is there some invariant for SL2R?
And yeah, because in this framework, you will not see SL2R because everything is vanished. The SL2R connection will vanish if we think about the limit. So now let me say we have explicit formula for GPPV invariant, and yes, please.
So the SL2R connection vanished only for this also for other.
It vanish when we think about all the limit when Q goes to O rational. No, sorry. When we only think about this. Oh, good question. Remind me something. So when Q goes to the primitive root of unity, but other root of unity, not maybe that's related to the Chen-Yang conjecture. Integer number. Any okay, so we have explicit formula here. We have explicit formula out on the boundary. Then we can think about this arrow. So let me say this arrow is correct. But the first step is to use some resurgent field. So it's not very easy to compute directly compute the limit. So what we use is a formula like this. So we have a linear combination of invariant and this O theta function, and we have a formula for theta function in the previous paper. So this is asymptotic behavior when power goes to 0 from upper of flat. And let me remark a little bit here. When mu is 0, when mu is 0, it's something like a modular form. If f has some certain parity, and the mu is 1 is something like a modular form. But when mu is 2, number theorists don't want to understand it because it's not modular form. So and we think it's very convenient to get all general form here because by using resurgent theory, there's no difference. We get this formula, and we are very happy that you can use this formula with this.
What is L?
What is L is the L function.
It is the L function.
It is L function, but you can evaluate it at negative point by using a negative combination.
Yeah. Okay.
So previously you give another formula for this GPPV invariant, then you give a second formula. What's their equivalence with either to check or is a very different things.
It is so just compute out this kind of. Yeah. So this is a form like a perfect figure. Yeah. But is a complicated coefficient.
In this theta function related to some Conjecture block of CIT?
I think so. I think so. It should be good.
The mock module.
This is not mock, this is quantum model form.
Uh,
But you can think about the inverse when you find it. So I was maybe I can say something about that in the end.
okay.
So this is the theorem we prove. We prove for any rational point. We think about the limit is WRT, and there's some normalized term. And this theorem is what I said before. It's the radial limit conjecture holds when we think about the plumbing manifold, and we prove when Q goes to any primitive.
So it's not just WR, right? Because the WRT is the cyclotomic number, right? You can apply WR to root of unity.
WRT is inside of
Joint.
this. And you can use.
And then you use okay.
Yeah, but there is some
Yes, some term. What is
numerical things to check. Number theory to check. So this phi is you want to ask this stuff.
Yeah.
Phi is the
okay.
rational number related to the breaking stuff. Okay, so next arrow is about resurgence. We think about the Ofuki series. Ofuki series highly related to this stuff. So this is when tau goes to 0, we just sum up all these kind of series we get with this series.
This is probably the comment on how to do the resurgence theory to prove something common. And how to do this. For example, know the resurgence for this GPPV invariant, and how to use the resurgence theory to study this the limit of GPPV in WRT.
Okay, briefly. Okay. So actually I prepared another slide for results, but here I can say if you have a partial set of fields, for example 0, this is out. Let me say this example. So we know this is equals to the Laplace transform. This is average Laplace transform of a Barrow transform of state field. So this is the OTP series. And the Barrow transform of this divergent series, we know it has a similar point on the Barrow plane. It is only along this positive imaginary part, and we think about this direction and this direction, and divide by 2. So this is the result. And once you can write a form like this, you can say it has a asymptotic behavior of this divergence. Yeah, when tau goes to 0 from upper half. This is a Barrow. So this is a Barrow plan, and this is tau plan. So tau plan, you can think about the limit from upper half plan to this point, and think about the derivation of such function and the limit to that point. Then you get this certitude. What is the question? The question is about
How to use
the limit. Yes, the limit is the first order. So the limit is exactly the first order. So we take n is 0, the first order of the limit. This is for generalized. So this is for any order. I mean, yeah, the limit is the first order, and the second order is about the derivation. Yes, so this is something about the result of. So here we have this form, and we can think about. We can think about L this direction minus L direction over 2. So we know the average sum equals to this. This is only, we can expand it out. This is exactly the average sum. And this is the Stokes term. And this is the analytic part. So this is why we have such formula. And another point of view is to think about the quantum modularity. This is modular because we change tau to minus tau inverse. And if you think about the difference, this is weight. If you think about the difference between the two functions, you get an analytic function, which is better than before. So we say this is quantum modularity property of the function. And these are formulas for μ1 and μ0, and for higher means we use so-called alien operators to compute the Stokes terms. So this is something else. I will give a brief introduction later for the alien operator. So in the end, this is generalized. This is general for anything private. And you think about the difference between the hat, which is inside, and that for Laplace is something else. So this is, so if we think about top line, this is the hat function, and our Laplace is something here. So we are thinking some function in this region, and the result is such. So this is made by the resurgence property of the series. It is not very easy. Proof is technical. But here we can see that this is technical part, but we can arrangement this to this line by thinking about the transcendence value. When we talk about SL2C components, this is the label of the SL2C component, and we divide it by using this SL2C component. This is some set. We call it a Hamid set because Hamid is the first one systematically understand this set. So later on we will see some good problem on this set. This moment, let's go to an example. So for sigma 237, for GPPV invariant is very easy. It's only one hyperset series. And it's like this. Fn is the periodic function. It's 84 periodic function. And it's out. So the authority series is like this. It's not very difficult to compute. And then we think about the Stokes or resurgence property of authority series. So we get the difference between this guy and our Laplace is this. So this is the Stokes term, and f hat is the discrete Fourier transform of f. So after the discrete Fourier transform, we get 3 different kind of periodic functions, and they are all 84 periodic. And these 24 numbers are distinct. And moreover, they have a very good property, and I'll show you later what is a good property, so why we want to understand these activity in this way. But now we can see that after some appropriate arrangement, you can see again 1 to 2, 1 to 4, and 1 to 6. So these labels relate to the SL2C connected component. Okay, so this is a very rigorous proof to say that once we compute the Stokes term, it really connect to the SL2C connected component because we didn't use any conjecture. Okay. So one remark for the number theory is that these 24 numbers are the only 24 numbers which is co-prime to 2, 3, 7 in the first 84 number. So as a result, we can say like this. So the difference in the end is a form like this. Okay. We can write it in the form of SL2C connected component. Okay, so this is the error of resurgence. Any question about this part? Okay. If there's no, I go to the last part. We think about this limit, which means that we have the Stokes terms, and we think about the limit of the Stokes terms, and we hope in the end some of them vanish and some of them survive. And the vanishing term should relate to the SL2R representation. So generally, the result is like this. So when we think about the limit of the difference with the Stokes, then at the beginning we divide it, we have a decomposition by using SL2C, and we think about this non-tangential limit is this minus minus k u and some periodic function. This is tau goes to minus k and theta tau of theta of the from upper half plane and non-tangential. This means that you have an upper half plane. You think about the limit to k minus k. We don't want to it turns to this point tangential. We don't want this kind of curve. And you can say like this: we fix any sector inside the upper half plane and think about the direction limit from upper half plane inside this section. This is the same definition here. So here on this side, we do nothing. We just think about the limit, we change the function. And here, this is the magic thing. So when you think about the limit, in the end, only depend on the SU2 connection. And let me show you.
So why can you? So you're saying you can the theta with negative k is equal to the theta with 0 multiplied by e to the k assignments?
Yes. Later on, I will give you one example. So you can move this k out. It's a good point. Okay, so equivalently, we prove this. So you can see this will be 0 if this L relate if this L satisfies this condition. And this condition is really the SL2C to SL2R condition. Okay. For this example, so let's think first that this is really 0. So this is just a limit computation. This is real. You compute the L function because you have the asymptotic behavior. You just need the first term. So compute the L function, you get 0. And it means that we have only 2 terms. And these two terms, you can write it to be this and this with some constant. So then we do the computation here. For example, for the first one, we want to understand what is the non-tangential limit of at minus k 0 with some periodic function. So at this moment, let me use f, and later on it is not. Okay, so the result is this equals to, we think about tau goes to 0, say the function tau minus k 0 f. So this is same. And I use a definition of theta function here. Tau goes to 0. This is f n exponential pi r n square tau over 2p. 2p is 84. But if I product 2, I get 168. And another term is 2 pi r n square. Okay. And f is that one. So f is related to 1 to 2 plus. And what is 1 to 2? We have a form like this. This is f. And you can see the support set this is why we organize like this. So because, for example, support set is 5, 19, 23, blah, blah. So you think about the square of the support set. So this is 25, 1, 6, 1. So this is something. And you compute the difference. The difference is 3, 6. So it is an integer multiple for 1. So this is why you can pick this term outside. So this is why in the end we get this is a number, and this is something like exponential minus 2 pi I k. This is 25. So this is why we have this kind of formula.
So this number 84 is 2
times 2
Yes.
right. And 237 appears in the in the fibers.
Yeah.
Like that's literally the 237.
Yes, it's exactly the same.
Okay. And 2 is because we have 2 as U2 components.
I mean, these two,
This 2, yeah.
this two is not from, I don't know, but yeah. Okay. Maybe it's no. Okay, so in the end, we get the asymptotic extension conjecture. So we think about the limit until it goes to exponential pi over k, and we know this type of subject is the real limit to that. And this guy we can compute it out. So because this is a magnitude function and it is holomorphic on the real axis, we can take the limit to get this one. And here is two Stokes terms. So if you think about the asymptotic behavior, this is the asymptotic series, and these are two polynomials with an oscillation term. So this is the proof. So I'll talk about some byproduct. The first one is the modularity property of GPPV. This is because when we compute the difference, we get Stokes, and the Stokes is really related to this minus tau. And if you have mu not equals to 0 and 1, you have something called a higher f, well, controllable. So this is some terminology, but the philosophy is something like that. You take the subtraction between the original function and the function on the S top, then the result is maybe not zero, but it is better than before. That's enough. And the second byproduct is a relation to the Habiro element. So I give some brief introduction here. So this is UN, of course you know it, and this is the definition of the Habiro element. So think about power series. If this is Q to N, then you get a power series here Q to N. This is easy version of the projected limit, but here we are not taking Q to N. We are taking some strange polynomial. Think about the limit of such range. Then we get this form, but it's not uniquely determined. Maybe it has some, maybe you have some G such that they define same elements. And moreover, Q inverse is invertible. So Q is invertible. Q inverse is a Habiro element inside this ring. So some literature will say this F and Q is contained in the V Q inverse. So see the literature. So I give some easier version here. The proposition of such element is like this. So first we can take the evaluation on the root of unity because this is termed. Okay, so the evaluation is easy. And moreover, if we have what is that? And moreover, this is a ring homomorphism. The point is this ring homomorphism is injective. So if you have all the values on the root of unity, so like this, if you have all the values on the root of unity, and the result is to say there is only one Habiro element satisfies the evaluation on the root of unity is, but maybe there is not. So it is injective, it's not surjective. And actually it cannot be surjective because there's another formula proposition to say if you find a dense set on the root of unity. So here dense is another topology, it's not the topology on this, it's something else. And if you find a dense set, that's enough to determine one Habiro element. So it's not subjective. And the next proposition is about the Taylor extension of the Habiro element. So you can think about the derivation of the Habiro element. You think about this type, and you take the derivation, and it is still a type of this that you have to arrange it. So once you have a derivation, you can think about the Taylor extension. You just take the limit. This is first order. You take the derivation. You take the limit. This is second order. Blah blah blah. So you have a power series in here, and all of them is contained in V too. So result is to say V is an injective map, which means that if you think about, for example, here you think about the power series at 1, then this is enough to determine one Habiro element. You don't need to think about other point, only one point, and think about defining many order ABCD. Okay, so the theorem related to us is for the integral homology sphere. If you have an integral homology sphere, the result is to say there exists a unique element in Habiro element. So the existence is not easy to show. You have known that it's always injective, but it's not survective. But for integral homology sphere, so if you have a WRT invariant on the root of unity, there exists one Habiro element such that the evaluation of that element is WRT invariant. Okay. And moreover, if you think about the Habiro element and think about the Otsuki series, think about the Taylor expansion at one, then that is the Otsuki group. Well, it matches very well with the WRT. Right. So this is the last theorem I want to show in this talk. So the talk, the theorem is to say, if we think about the GPPV, we can say the asymptotic behavior when inside the unit is to the root of unity defines Habiro element. This is not very trivial criteria because you have to think about every expansion. So because we say every expansion defines an element, and they should determine one Habiro element. So the result is to say this GPPV invariant really determines one Habiro element, and any asymptotic expansion of GPPV invariant at root of unity equals to the Taylor expansion of the Habiro element. And moreover, each series is resurgent. This is some further study about the model part. So this is there's no question. So at the beginning, we know Ramanujan invent mock theta function, and it's 21 or 17 mock theta function in his last letter to Habiro. And the people like to understand the asymptotic behavior of the mock theta function at that year. But I think the most important work is by Zweger, who is a student of that year. And he wrote a thesis about mock theta function. He gave a framework for mock theta function. So he said that mock theta function is just homomorphic part of the harmonic mass. And this is an analytic function. And this is not, this is a real function. And this is really a model form. This is not exactly model form. So he said that if you can find a non-homomorphic part such that the sum of these f plus and f minus give you a model form, then we say the homomorphic part is the model form. That's the model form. And he proved that at least for when we're looking at the first 17 examples, that all satisfy these properties. But later on, there's some further study of this framework. So here, this is some arrows in harmonic mass. So if we think about this CK, this is a very special kind of operator in harmonic mass form. So we see this is a magic operator. It maps a non-homomorphic non-model form to cast form. So it's so this is a cast form that is homomorphic, and it has it vanish on the boundary and it is model. So it's a very magic operator here. And moreover, you can define different kind of actual integrals to find back these minus and mu things here. So what I want to say is GPPV invariant is actually here. this is the GPPV, right? It is a quantum modular form. And what we did is some error from the resurgence to this GPPV invariance. So nowadays there is a very, I think it's important conjecture in modern form to say the modular function relates to this quantum modular form only by substituting Q to Q units. This is another theory. I have an example here. This again for 237. So these are the modular form invented by Ramanujan. And they are all, so Ramanujan call this seventh order modular form. And if you substitute the form, if you find a form like this, you can substitute Q to Q units. For example, here, this is again a form of Q series, but you cannot substitute it. This is mean for any project Q square over 4p. This is GPPV invariant. If you directly substitute in, it is nothing. You just reflect everything outside. You say nothing. But here is something else. So if you have a form like this, when you substitute in, you still get a homology function inside. So this is a point. And the result is to say that if you substitute in the end we get a GPPV or quantum modular form. And these are three different kind of. So you can see this is really the block we use, and it is related to the.
So why does did Ramanujan say 7 order? So where's 7 in this three things?
Yeah, 7 is about this total subgroup.
Okay.
Okay, so this is the first part. Do we have time for the second?
We probably got shape for another time. Or
Maybe you can, how long does it take?
Maybe 40 minutes.
maybe it's good for another talk. Yeah. We can schedule you for another.
Yeah. So, that's it. Please.
The Habiro element can be only defined for the integral homology.
Oh, no, it has version, version from the superior, and it has another semi group information. But at the beginning of it has only a formula like this, like this is other further work. Some of them is not by Habiro.
Harley. Yeah. Harley. TH.
Work in this.
Ask about Conjecture and Conjecture to directing 4D. Because there's recently this result which says that like if you give me WRT as a TPFT, I can extend it to a like 432 TPFT, which is Conjecture basically. You can generalize this construction to use like a non-simple modular tensor category. You can use this Conjecture thing in the bulk to define as a boundary condition this non-semi-simple WRT stuff. So I'm wondering like how, like maybe there's also a way to use resurgence to study Conjecture as well. With Conjecture is like a lot of people say this, that Conjecture is related to quantum gravity, and there are some problems. So it's there's still problems with using Conjecture to study quantum gravity. Like there's this flatness problem in 4D quantum gravity, which they kind of take the limit kind of incorrectly, and then they're only able to get out flat solutions. Possibly, yeah. Maybe resurgence would help us like take the right limit the correct way. But yeah, I was wondering if we can maybe extend this technique to critical higher dimensions. What do you think?
I don't know, I guess depend on the expression. Yeah, the Seifert theory is really depend on the expression.
Okay.
First is to prove the principle.
Mhm.
So what's the difficulty of extending the cases from the Seifert quantum sphere to other cases?
Which kind of topic?
Like the Plummer manifold?
The fundamental, I don't think there's so many difficulties. Because in the end, all of them is something like partial theta series. But the problem is maybe the coefficient part is more difficult. Yes.
But for hyperbolic manifold,
For hyperbolic manifold, that is a problem.
because
We don't have the full series. We don't have the full series.
I see.
Yeah, we cannot write down the closed form of the OCP series. Some of them is numerical. For example, Jiegu have some results for first maybe 50 coefficients, and he use Bade extension instead of borrow Laplace. And in that form, he can guess what is the transcendence value, but it's not easy to see the other order. So on the bar plan, it is not easy to see a singular point behind one singular point. So this is a problem.
Is this because the hyperbolic manifold the BPV is written in terms of quantum? What's so for manifold that you have discussed today, the usually invariant is written in terms of the beta function, and hyperbolic manifold they are not written in terms of the theta function. No. What's the big loss there?
I don't quite understand. That relate to this. That relate to this guy. So he has some definition of GPPV variant. Hyperbolic modes.
Listen to Jeffrey's talk once, right? He did some resurgence analysis for dimensional function.
That will complement our degree.
I see.
Yeah, there's some resonance property of dialogue. There's no problem, but I don't think it's very easy to generalize to the GPPV route. For each dialogue with there's a problem.
Any more questions? If there's no more questions, thanks for speaking.